The thing that I've always found amazing about chemistry is it's an entire field of science that we as human beings have developed to understand what is happening at an almost unimaginably small scale. In particular, we're going to be thinking about the atomic and even the subatomic scale, and by looking at that scale, we can begin to understand the universe in which we live in, the scale in which we live in, and even to be able to make predictions about what will happen. So to operate at this small of a scale, we need to appreciate how small of a scale it really is. We're going to have some units of measurement, and this video is going to focus on mass. How do we measure mass at such a small scale? Well, to do that, the chemistry community has historically used something called the atomic mass unit. It's historically denoted as AMU, and the more modern version of this is the unified atomic mass unit, that is denoted by just the letter U. So how does a unified atomic mass unit connect to our units of mass that we might use on a larger scale, like grams or kilograms? Well, the unified atomic mass unit is defined as 1.66 times 10 to the negative 27 kilograms. So when you see something like this, it's hard to comprehend just how small it is, as it would be 0 point and then 26 zeros, and then you'd have 166. So a very, very small and really unimaginable number that we can only try to extract within things like mathematics. The other thing you might realize is this feels like a bit of an abstract number, 1.66. Why did they define it that way? The answer to your question is this definition makes it a lot cleaner when we think about the mass of an atom or other constituents of an atom, like a proton or a neutron. Roughly speaking, the mass of a proton is one unified atomic mass unit, and the mass of a neutron is approximately the same mass of one unified atomic mass unit. The electron's masses are smaller than either of these. It's actually almost a 2,000th of a proton or neutron, and so you can imagine an atom which is made up of protons and usually neutrons and electrons as well. The mass is mainly going to be the protons and neutrons in the nucleus, and so if you know the number of protons and neutrons inside of the nucleus, you're going to have a pretty good sense of its atomic mass. You can actually see this indicated on a periodic table of elements, which we have here. We will study the periodic table of elements in a lot more detail in other videos, but you can see a couple of interesting elements. When you have the abbreviation of a given element, such as H, it represents the name of the element, which in this case is hydrogen. The number on top of this periodic table is an atomic number, and that tells you how many protons it has, and an element is defined by the number of protons. Any atom that has exactly one proton in its nucleus is going to be hydrogen by definition, and any atom that has exactly 20 protons in its nucleus is going to be calcium by definition. And this goes for every amount of protons and their corresponding elements. So what exactly would we expect the mass of a hydrogen atom to be? It actually turns out that this is not an answer that can be answered simply, as there are different versions of hydrogen that can have different numbers of neutrons. Most of the hydrogen in the universe actually has 0 neutrons. There are versions that have 1 or 2 neutrons, but almost 99.98% of hydrogen in the universe has 1 proton and 0 neutrons. And if it's a neutral hydrogen, it's going to have 1 electron as well. When we talked about versions of a given element, there's a fancy word for it. They're called isotopes. And the different isotopes all have the same number of protons because they're the same element, but they have a different number of neutrons. So if this is the most common form of hydrogen, what do you think its mass is going to be? Well, its mass is going to be essentially the mass of a proton plus the electron. And roughly speaking, it's going to just be the mass of a proton because the proton's going to be so much larger than the mass of an electron. So you would expect that its mass is approximately one unified atomic mass unit. And if you were to precisely look at the mass of a proton and an electron to add them together, you actually get something that is a little bit closer to 1.008. And you actually see that number right over here on the periodic table of elements in the hydrogen box. Now this number, although it's pretty close to the mass of the version of hydrogen that I just described, is actually a weighted average of the various versions of hydrogen. It's just close to this version because this version represents most of the hydrogen that we actually see around us. If, for example, you had two versions of a hypothetical element, let's say 50% of the element that we see is version 1, and version 1 has a mass of 5 atomic mass units, and then version 2 is the remaining 50% of what we observe of that element, and it has an atomic mass of 6 atomic mass units. So if we did the math and got the average mass of those two isotopes, you get a weighted average of 5.5 unified atomic mass units. So that's actually how these numbers are calculated. They're not just the mass of one type of that element, they're actually the weighted average of the various isotopes, and so this number on a periodic table of elements is known as the average atomic mass. So as we'll see as we continue diving into chemistry, this fundamental concept of average atomic mass and relative atomic mass, which we will soon cover, will be very important to know and understand in order to gain perception of the incomprehensibly small scales that we work with in chemistry. So in the next chemistry video or two, we'll cover the atomic aspects that we analyze in a chemistry lab, such as the mole and Avogadro's number. But for now, I thank you all for watching.